All right, let's go and review some things we talked about in our last lesson. We began talking about our third major conic section class, that is the ellipse. And an ellipse, remember, is basically like a distorted circle. Take a circle and either smush it down or squeeze it in, right? If you squeeze it in, then the ellipse is taller than it is wide. If you smush it down, of course, it's wider than it is tall. The ends of a wide ellipse, or the top and bottom of a tall ellipse, those ends are referred to, class, as the vertices. Good. We have two vertices at top and bottom, or end and end, depending on how the ellipse is shaped. And if you were to connect the vertices with a straight line, that line is referred to as the major axis. Of course, the midpoint of the major axis is called the center. It's the true center of the ellipse. Now, again, all the points aren't the same distance from that center point, but it is the center of the ellipse. And if we were to put a perpendicular through the center that stops at either the top and bottom or sides of the ellipse, that line is called the minor axis. Algebraically, how do we represent the length of the major axis? Good. The major axis is 2a, and the minor axis is 2b. There are two really important points in the ellipse that really define its shape. And those points are referred to as the foci. And remember, at any point along the ellipse, it doesn't matter what point you take, if you measure the distance to one focus and the distance to the other focus and add those two distances, that sum will always be the same at any point for that particular ellipse. How do we represent the focal length, the distance from the center out to each of the foci?
The square root is half plus b squared.
Okay, that's how we find it. We take the square root of a squared minus b squared, but it's represented by the letter C. It's represented by the letter C. Remember that the major axis is 2a, from center to vertex is a, center to the other vertex is a, for a total length 2a. 2b is the total length of the minor axis, so that's from center down and up to the end, to the sides, if you will, of the ellipse. That's 2b. And so if we were to take just the a value squared, just the b value squared, subtract those, take the square root, gives us the focal length. Through each of the foci is a focal chord called the latus rectum. But since there's two foci, there are two latus rectums, but we don't call them latus rectums, we call them the, do you remember the plural? Latera recta. Say that with me, class. Latera recta. And as before, we generally notate the half latera recta length as opposed to the full latus rectum, because graphing purposes, right, that doesn't really help. How do we find the half latus rectum?
B squared over a.
Good, b squared over a. The whole latus rectum would be 2b squared over a, but since we're just doing half latus recta, our latera recta will be b squared over a. The shape of the ellipse, remember, is described by a ratio of distances called the ellipse's eccentricity. By the way, our new junior high science book, I was teaching junior high astronomy the other day when y'all were on your field trip, and they actually started teaching 8th graders and 7th graders about eccentricity. Now, their definition was how funny shaped the ellipse is, right? Because they talk about planets going around the sun in ellipses, right? First time you heard that wasn't in my physics class, I don't think. And so they said the weirder it is, the more pronounced or elongated it is, the greater the eccentricity. The more circular it is, the lower the eccentricity. That's as far as they went, but they're at least introduced to the term now in junior high. So if you're watching this like 6 years from now, you're like, yeah, I learned that in junior high. See, look at that. But how do we find the eccentricity for an ellipse? C over A. You take the focal length divided by half the major axis, and of course the focal length is always smaller, right? From center to focus is always smaller than center all the way out to the vertex. So that means C, since C is always smaller than A, the eccentricity always lies between what two values? 0 and 1. Theoretically, a 0 focal length, meaning the foci are both on top of the center, making it a circle, would give you the eccentricity of 0. If the foci were to fall on top of the vertices, which would give you a perfectly straight line, that would be 1. Well, it wouldn't be an ellipse with an eccentricity of 0, it'd be a circle. It wouldn't be an ellipse anymore if it had an eccentricity of 1, so we just say between 0 and 1 are our eccentricities. What is the form, the elliptical form that we're trying to get our ellipses into, Jamie?
squared over, or y squared over b equals 1.
Really close. Quentin?
Square root of A and B.
Right, x squared over a squared plus y squared over b squared equals 1, but the key is you do need it equal to 1, and you need plain old x squared and y squareds in the top, with different values underneath them, of course. The key, of course, is that a squared has to compare to b squared. How, class?
Yeah, it's B squared.
The a squared is the bigger number, the b squared is the smaller number, so wherever they happen to fall. So it's possible you get x squared over b squared plus y squared over a squared equals 1. It's just whichever one's bigger is the a squared, whichever one's smaller is the b squared. And of course, that'll tell you whether it's tall or wide, right? Last of all, how do we define, and I kind of referenced it a little bit earlier, how do we define an ellipse in terms of a locus? Jamie? This one's really hard to phrase, so I'm rather forgiving, to be honest, on the phrasing here.
Like the set points equidistant from 2 given points.
Not equidistant from 2 given points, because that would be a perpendicular bisector, right? Not equidistant from 2 given points. Quentin?
Equal angular? No.
It's the locus of points having a constant sum of distances from 2 fixed points. The sum of 2 distances, the distances from that point to the 2 fixed points, that sum remains constant. So something about that, like, and yet the locus of points that if you measure the distance to one point, the distance to the other point, the sum of those 2 distances is always going to be the same. I would take that, right? It's a more wordy, but it says the same thing, right? And again, admittedly, that one's a rather challenging one to word. Let's take a look at the homework now and see how you did on page 245, number 1A and 1G. 1A, they gave us 16x squared plus 25y squared equals 400. Now this is loosely somewhat in a conic form, not entirely. But the key, remember, to getting the elliptical form is I've got to get the equation equal to 1. And how do I get it equal to 1 here, Jamie?
Divided by the 400.
Divide away a 400 from everything. And of course, that gives us the first thing I really care about, and that's the 1. Next of all, though, I've got to have the x squared and the y squared by themselves. Now, again, the fact that I have different numbers to begin with tells me I'm going to end up with different numbers down here, which tells me it's not a circle, right? Matching numbers, circle. Differing numbers with the sum between the x and y squareds, we end up with the ellipse. But I've got to have just a plain old x squared, which means even if I can't divide a 16 out, I have to anyway. That's really obnoxious. I have to divide a 16 out of the 16 and a 16 out of the 400. Conveniently, it works evenly to give me
25.
25. Here, I have to divide a 25 out of the top and bottom, and conveniently, it gives me a 16. Does it always work perfectly like that? No, but usually the book is kind to us. For instance, if I had a 4x squared plus 27y squared is equal to, I don't know, 81, for instance. Well, I'd have to go through and divide everything by 81, and that doesn't work so well, does it? Because I divide a 4 out of the top. Can I divide a 4 out of 81? So I would end up here with x squared over 81 fourths. Can I divide a 27 out of 81?
Yes.
Yes, actually. I'd get a y squared over 3 equals 1. Okay, so, I mean, could it work out weird like this? Yes. Normally, the book's going to give you things that work out with integers, and that's awfully nice of them. All right, so let's take a look at this here. So ignore the other. That was just for illustrative purposes. We said that for now, the center of our ellipse is going to be at 0, 0. And as with all the conics, right, we start with the 0, 0, and we go from there. The next thing we want to determine is which axis is the major axis going to be. And how do I tell which one's major again, Jamie?
Which one is bigger?
Which one has the bigger number under it? Not which one is bigger to begin with, but which one has the bigger number under it now. In fact, that would be the opposite of which one is bigger to begin with. Which one is the major axis, class?
X.
The x-axis, because it has the larger number beneath it. Then we need to find the length of the major axis. And remember, this bigger number is a squared. So a, class, would only be 5. And that's one way you could phrase the major axis length. You could say it's 5 on each side, or you could say it's got a length of 10. Either answer is acceptable. Though, I can't remember perfectly because it's been a year since I taught this, right? But I feel like on the quizzes I ask how long is each side of the major axis. If it's phrased that way, you definitely want to say 5. If I say how long is the major axis, 10, or you could say 5 each, right? But make sure you're checking the wording. And of course, when we get to quiz time and test time, I'll point that out as we go over the quiz or test to make sure we emphasize. For now, since I don't remember, I'm too lazy to go look it up, I'm just going to show both ways. All right? How about the minor axis? How long is the minor axis, class? 8, or you could say 4 on each side. Again, this is the b squared, therefore b is 4 each for a total length of 8. Then we want to find the focal length. Now here's where it's awfully nice that we have the squares showing, the 25 and the 16. Just to find the focal length, remember we're going to subtract the squares and take the square root of that to get what focal length? 3. And then finally the half Latus Rectum lengths. Remember that's going to be your b squared over a. b squared is 16, a is only 5.
3.2.
Good, 3.2, or you could say 3 1/5. So it comes out evenly to 3.2. Did we get the analysis correct on the first ellipse? Then let's take a look at the graph and see what it should have looked like. Again, the fun part here is making sure it looks more like the oval and less like a football. Sure we don't get pointy ends on the ellipse. That's the challenge with which we are presented. All right, so first of all, of course, the center at 0, 0, no problem there. Along the x-axis, we're going to go 5 each direction. So out here to the 5 and out here to -5. Up and down, then we're going to go 4 in each direction. Now notice the minor axis is almost as long as the major. That's going to make this a more circular ellipse. Okay, focal length 3. By the way, you didn't ask for it, but what would the eccentricity be here? 3/5. Focal length 3, half major axis 5. So 3/5 or 0.6. That's still technically closer to 1. So still not even in the range of ellipses you could have. It's on the less circular side, and yet it still looks somewhat circular here. We're going to go 3.2, remember, up and down perpendicular to this major axis. So up 3.2 and then down 3.2 from each of the foci. Again, if we wanted to label, here's a vertex, here's a vertex. Of course, here's the center. Focus, focus. Latus rectum, latus rectum. Remember, the ends of the minor axis don't have a name. My recommendation, remember, is to start at the vertex, just like you were graphing a parabola, and slowly curve until you're just about head on. Just as if it's coming in straight in here. And then again, kind of like we did with the parabola, I'd recommend we retrace to get the nice smooth curve. And just coming in here, I might have come in a little early actually on this here. So maybe a little bit more like that. And this is one reason why pencil is preferred, especially on quizzes and tests. Retrace here. And if you wanted to, you could even retrace over these, just kind of smooth sides out a little bit. And end up with an ellipse that looks something like that. Again, you're looking at it, and a small child would say, hey, is that a circle? Even a small child would probably say something looks funny about it, right? So no, not a perfect circle, but you can tell it's more circular than some of the ellipses that we've done before. How do we do on the first ellipse for letter A?
Got it.
All right, any questions? Well, let's take a look at letter G. We'll go with yellow on this one for contrast. Let me zoom in just a little bit. All right, letter G. We have a 9x squared plus 4y squared equals 36. And Quentin.
A squared plus, or a squared over 34 plus y
Over
squared
who?
4. plus y squared over I equals 1.
There we go. We're going to divide a 36 from everything. 36 divided by 36, 1. 4 36 becomes a ninth. 9 36 becomes a fourth. Center again was at 0, 0. Which axis is major, class?
Y.
The y-axis this time. How long is the major axis?
6.
6, or we could say 3 each, and there we see the 3 as the square root. The minor axis?
4.
4 or 2 each. Of course, here we can see the 2 as the square root. The focal length is going to be?
About 2.2.
Yeah, the square root of 5. We subtract the squares and take the square root, which is going to be about 2.2. And then the half lateral rectum, remember, is going to be your b squared over a. Well, there's your b squared. Your a is a 3, so we end up with literally
1.3.
4/3, or we could say that's about 1.3, 1 1/3, right? So once again, your center here at 0, 0. You're going to go up and down 3 to the ends of the y-axis. We're going to go 2 over on the x-axis. Up and down 2.2 to the foci. By the way, then, you would have square root of 5 over 3 for your eccentricity. What is that decimal value? Square root of 5 divided by 3. Focal length divided by half major axis.
0.745.
0.745. So yeah, you're looking at a value that's 3/4 of the way towards straight line. If you're so a little bit more pronounced ellipse here. And then 1.3 over, again, the major axis runs here between these two vertices. So we're going to go out 1.3 in each direction, and out 1.3 in each direction. And I'm going to start at the vertex and slowly curve here. Retrace so it doesn't get too pointy, and slowly curve here. Slowly curve there. Gonna do a little bit of a retrace and curve up there. And we get something like that. That, I don't know, that almost looks more like the eyeball, maybe a cat eyeball, right? Because the cats have that narrower pupil. It's got a little cat eye staring at you there. How many had this for letter G?
Very close. I have 4. Mine. I had the same focal length for the last rectum. I think I did 9/2 instead of the.
Oh, you did a squared over b instead of b squared over a, right? So the little number over the square root of the big number, if you want to remember it that way. All right. So that would have been very weird then, because your lateral rectum would have been out like 4.5, and you're like, how do we connect all of this, right? Looks like a butterfly by the time you're done. All right, questions? All right. Go ahead and do 1D. Go ahead and get out a new Cartesian plane started, and let's do number 1D on page 245. Number 1, letter D. Give you a little bit of a head start, and then I'll graph it also. check your analysis on 1D. Questions, comments? I'm going to put the graph together, or finish putting the graph together, I guess I should say. Once you're done with 1D, go ahead and do 1F. Any questions on the graph? Just a little bitty guy right there. Get a little bit of a head start on F. questions on the green one? All right, feel like we got the hang of this? All right, well, let's move on. The next thing in your notes, let's talk about the elliptical form for a translated center. The elliptical form for a translated center. And I'm curious, do either of you want to take a stab at what you would guess the elliptical form would look like? Either of you feeling adventurous? Not adventurous at all. Jamie's like, no, not after this go-get test. All right. How about x minus x1 squared over a squared plus y minus y1 squared over b squared equals 1. It's still x squared over a squared plus y squared over b squared equals 1, but it might not just be x squared or y squared, but x minus x1 squared and y minus y1 squared. Look familiar? It's what we did with the parabola. It's what we did with the circle. X squared became x minus x1 squared. And even like in the parabola, maybe a y became a y minus y1, or an x became an x minus x1, right? And of course, we understand those two could switch, right? Whichever one's bigger is going to be the a squared. So write this down if you would. X minus 2 squared over 4 plus y plus 1 squared over 25 equals 1. Nothing is changing except the center. The center this time isn't 0, 0 because it's not a plain old x squared and a plain old y squared. Instead, the center is going to be where?
2, negative 1.
2, negative 1. But everything else is going to stay the same. Which axis is the major axis, class?
Y.
Because it's got the bigger number under it, correct? How long is the major axis? 5 each. Or you could say 10. How long is the minor axis?
2.
2 each, or 4. What is the focal length? Radical first.
Square root of 21.
Square root of 21. Which is approximately
4.6.
4.6. And then, how long are the half latera recta? Fraction first.
4/5.
4/5, which as a decimal would equal
0.8.
0.8. Seem easy enough? Now, if we were to graph it, my suggestion would be this. Plot your translated center first, and then draw a prime axis. Sound familiar? Right? So our center here would be at 2, negative 1. And I'm going to draw a new y prime axis. Make sure this is almost on the screen. And then from this center point, up and down 5. From this center point, out 2 in each direction. Let me erase the old ellipse so it doesn't confuse. Don't really need that in our lives right now. All right, and then our 4.6 focal length is along the major axis, remember? So 4.6 and 4.6, and then there we go out 0.8 in each direction, and get a rather slender ellipse. Like this. But you notice it's just shifted off the origin now. It's been translated to 2, negative 1. Write this one down. X plus 3 squared over 36 plus y plus 2 squared over 16 equals 1. Stay with me. The bell's going to ring here in just a moment. Stay with me through the bell if you could. Give you just a minute or so over. What's the center now?
Negative 3, negative 2.
Negative 3, negative 2. Down into that third quadrant. The major axis is? X-axis. Now again, it's going to be an X prime axis, right? But yeah, we'll say the X-axis. Major axis, length? 12. 6 in each direction. Minor axis, 8. 4 each side. Focal length, subtract, take the square root. Square root of 20, which is, let's see, 4.6 was square root of 21, so 4.5 square root of 20?
Yeah, 4.5.
And then lattice rectum length, b squared over a.
2,
Fraction
16
first.
over 6.
16.6, which becomes approximately, stay with me,
2 and 2 thirds.
2 and 2 thirds, so 2.7-ish. All right, so again here, I'll show it in yellow for the graph. We go back 3, down 2. If you want to just throw a quick sketch with me on your graph, on your Cartesian plane you'd already used. -3, -2. Draw a new x prime axis. Along that x prime axis goes 6 in each direction from this center point. And just all the way to the back end of my graph. We'll go up and down 4 from the center point, out 4.5 to the foci, and from the foci out 2.7 in each direction. And not taking a lot of time to draw it super neatly, but just a quick sketch, something along those lines for our ellipse. All right, questions on how to handle a translated center? Seem no more challenging? All right, well for homework you have 2 graphs to do. I want you to do page 245, 1E, and 10A. Page 245, number 1E, and number 10A. And we'll take a look at those in our next lesson. Have a wonderful rest of your day, and you are dismissed.